Welcome to the GlobalFoundries technical webinar, How to Maximize 14LPP and 22FDX Performance and Power Savings with Invecas IP. My name is Sean O'Kane from ChipEstimate.com. Today, we are pleased to introduce our speaker, Krishanan Subramanian. Mr. Subramanian is a senior member of the technical staff at Invecas, a partner in the Global Solutions ecosystem. Krishanan has 13 years of experience and expertise on a wide range of domains. He is responsible for the complete CAD automation design flows and methodologies for the company. Please welcome Krishanan Subramanian.
Invecas enables a diverse range of industries by offering comprehensive and optimized solutions such as logic and design verification, physical design, embedded software, silicon-proven IPs, testing, assembly, integrated supply chain management, and much more. So Invecas offerings are not only limited to the tested device chip, but go way beyond, helping customers for evaluation of board designs, reference design kits, or full-fledged embedded system products. Customers get access to the new ecosystem with Invecas as a single source of silicon-proven IPs, design, fabrication, packaging, assembly, testing, and much more. Invecas has expertise in delivering silicon-proven IPs. Our portfolio is wide and covers foundation IPs, interface IPs, and analog IPs. In foundation IP is a comprehensive portfolio of silicon-proven standard cells, memory and GPIO libraries optimized for power, performance, and area exclusively on GlobalFoundries advanced process to minimize integration risks, die costs, and maximum SoC design flexibility for a variety of applications. We have these IPs on both the GlobalFoundries 14LPP platform as well as the brand new GlobalFoundries 22FDX platforms. We have a rich family of optimized high-performance interface PHY IPs ranging from SerDes, DDR, LPDDR to MIPI and HDMI, enabling SoC designs for the consumer communications, mobile and IoT markets. Again, these portfolios are spread across the GlobalFoundries 14LPP, having multi-protocol SerDes, DDR3-4 PHYs, LPDDR 3-4 PHY, the MIPI D5, and the USB 2 OTG 5. On the GlobalFoundries 22FDX platform, our IP portfolio is comparatively larger, which is going to have additional HDMI, TX, and RX 5 blocks, and the MIPI M5 as an extra IP on the 22FDX platform. On the analog IP side, we have a growing family of silicon-proven analog IP for clocking, data conversion, thermal sensing, process monitoring, and other applications optimized for GlobalFoundries technologies. On the 14LPP GlobalFoundries process, we have the PLLs, thermal sensors, and the process monitors, whereas on the 22FDX platform, we have PLLs, thermal sensors, process monitors, and dual channel audio, ADC, and DAC, and triple video DAC. These are our offerings when it comes to foundation IP, interface IP, and analog IPs. The 22FDX is a 22 nanometer fully depleted silicon on insulator platform offered by the GlobalFoundries. The main motivation to look at this particular option is the ultra low power design requirement, which is driven by the wireless and portable electronics segment of the market. The major market requirement being wireless and mobile markets, IoTs, which require ultra low dynamic and leakage power. The high-end smartphone and processor, they require high performance, gigahertz performance range. Design performance is simply a product of process technology advancement or the capability of the foundry, which is GlobalFoundries, and circuit design expertise, various techniques and innovations, which Invecas is in the forefront. So we have multiple choices, a wide range of choices for product designers using this particular combination, where you have an excellent process set up by GlobalFoundries on the fully depleted silicon on insulator options. The devices, the simple range that we have in the selection of devices to be used in the designs, the VT options is tremendous. The transistors, which are fabricated, the channel length, oxide thickness, and various circuit techniques, and our topology that comes into the picture, where beta ratio and stage ratios matter a lot when it comes to the circuit design techniques. And we have a very robust architecture of multiple track heights and excellent layout architecture styles. And our SoC design techniques, including DVFS and backgate biasing, is well proven and absolutely ready for the industry to be explored. How does the 22FDX offering stand up against the market pulse? So the consumer industry requirements is perfectly met with adhering to Energy Star goals and enables small form factors. So thermal and reliability integrity as well of these processes enables a small form factor. When it comes to the wearable industries, wearable applications, longer battery lives, and RF integration to reduce the overall system cost, we have battery life which increases from on an average of 3 to 9 days while adding Wi-Fi and Bluetooth. The triple gate oxide in this process minimizes leakage power in standby modes. So we can look at devices where they are in the sleep option, and moments time it wakes up and then gets into gigahertz of performance. That's the kind of applications this particular platform offers, which is the future. When it comes to the IoT and industrial applications, you have the HD image and video, integrated RF and MRAM, and battery operations. HD resolutions with image processing, increased bandwidth for HD video, a 0.6 volt operations, and low leakage power capability for battery life. So one more important factor is it removes the fan for sealed enclosures, where thus by allowing small form factors, low BOM, and reliability. We can also have a look at low and mid tier mobiles, which means very good display, video, wireless needs without the cost of FinFET. That enables a lot of product designers to design better and efficient and cheaper products. On the auto and infotainment side as well, this is one of the processes which could do very well, mainly because of the low active current, the 0.6 operations, and better leakage profile at temperatures as high as 150 degrees centigrade, and simply because up to 40% of analog content, and FinFET is not required at all. So that's why auto and infotainment is going to be a very key market when it comes to 22FDX platforms in the future. The next application being Wi-Fi and RF applications, where we can simply achieve higher data rates at lower power. That's one of the keys when it comes to having a successful product and application being built. The 22FDX process, as a process, how does it stand in comparison with the bulk planar process and FinFETs? So planar process is very similar to bulk, about 20% lower 20% lower die cost than FinFET is what we are looking at when we are talking of FDX, 50% lower mask cost than the FinFETs. We have an integrated RF option in this technology, and this is architectured for transistor body biasing as well, where we can achieve ultra low voltage operation with the forward body biasing, and at the same time, with a bit of compromise on speed, we can achieve ultra low leakage with the reverse body biasing. 22FDX process is suitable for low voltage applications, especially for such as the IoT and wearable devices, where longer operation time is required out of smaller supply. FDX serves the purpose very well because of its obvious process features that are going to be listed out here. So when it comes to performance, if we keep the planar bulk transistor as a reference, 22FDX certainly gives a high performance, as good as the FinFET. When it comes to leakage, the planar bulk devices have high leakage. 22FDX has lesser leakage, whereas the FinFET technology offers the lowest leakage. 22FDX as a process is a planar process, which is very similar to the bulk process. It has about 20% lower die cost than the FinFET process and about 50% lower mask cost than the FinFET process. It has integrated RF options, and it's architectured for transistor body biasing, where in forward body bias mode we can achieve ultra low voltage operations, and in reverse body bias mode we can achieve the ultra low leakage options. Although there is a trade-off between both, we can certainly use the reverse body biasing and forward body biasing technique to suit our requirement and make full utilization of the process option in terms of performance and low power. 22FDX process is suitable for low voltage applications, especially for the applications such as IoT and wearable devices, where longer operation time is required out of smaller supply. FDX serves the purpose very well because of these obvious features, where low power and low leakage options are excellent in this process. How does a 22FDX stand in comparison with a reference of a planar bulk process and the already popular FinFET process? So when it comes to performance, if we consider the planar bulk process as the reference, 22FDX is certainly higher in performance, and FinFET certainly is at par with 22FDX when it comes to performance. The leakage in planar bulk, if that has to be the reference, is pretty high, mainly because of very small and deep channel beneath the gates, which gives less control of the gate itself, whereas in 22FDX we have good gate control over the thin channel, and also the leakage is less, as there is no parasitic diodes between the source and drain and the substrate, mainly due to the device construction itself. When comparison is made between 22FDX and FinFET on leakage, obviously FinFET scores over 22FDX. That's mainly because of you have the process itself the device itself is constructed in such a way that you get better gate control over the channel from all three sides, all three directions. That's one of the features of FinFET, which can be compensated if you look at the power. So planar bulk being the reference again, power is pretty low when you compare 22FDX with FinFETs, where it has high power. When you come to back bias on planar bulk devices, the scope is very limited, whereas in FinFETs it could be possible, and in 22FDX a very wide range is possible, right from minus 2 volts to plus 2 volts of back bias can be applied. Again, when it comes to power supply, we have an obvious advantage for 22FDX over the planar bulk as well as the FinFET process. Here it is much lower because of the option of applying a higher back bias, whereas in planar bulk and FinFET this is simply not possible. So this is a huge advantage that 22FDX offers. When it comes to channel doping, planar bulk, if you consider it as a reference, it is doped, whereas 22FDX is undoped, which stands very similar to the FinFET process. Scalability in planar bulk 20 nanometer, in 22FDX very much possible up to 7 nanometer based on the fabrication of required thin box and channel, whereas in FinFETs it can be scaled further down to 5 nanometer. Now when you compare the source drain in planar bulk, which is very normal, and planar 22FDX, the source and drain are a bit raised, which means there is an increased source resistance, which gives us better DIBL. In FinFETs as well, it is raised, but the only difference being we have low resistance of source and drain. Design porting is in planar bulk we have most of the designs. When you port these designs from planar bulk to 22FDX, portability is very straightforward and easy, whereas direct porting from planar into FinFET is not really efficient and sometimes impossible. So overall cost, if you look at the process of product development, with a reference of planar bulk, 22FDX is very low compared to the planar bulk, whereas FinFET, the cost is quite high. The overall cost is pretty high when it comes to FinFETs. 22FDX comes up as a very viable alternative for the applications discussed above. The key advantages being low cost, 20% lower die cost than FinFET, low process complexity, and fewer masks than the FinFET technology. Even extending Moore's law to it, there is a 20% die shrink and higher performance for 28 nanometer and below technology nodes. The main feature of backgate biasing helps performance and gives us adjustable power through body biasing, which is a forward body bias and reverse body bias. The ultra low voltage operations can be achieved through the forward body biasing and the ultra low leakage with the reverse body biasing. Overall lower junction leakage, ultra low voltage operations, you have steeper subthreshold slopes, lesser VT variability due to absence of the dopants in the channel, no random dopant fluctuation, unlike you in the planar bulk process, and the best part is you have high robustness due to better ion and I-off, the on and off currents of the transistor. The 22FDX technology fact sheet looks something like this. For LVT and SVT, both are formed in flip well, where PFET is in P well. Only forward body biasing is possible for these devices. These are supported to push the performance, that is the ion, the on current, beyond the no body bias or the no BB conditions, at the cost of increase in leakage. So if we this is a trade-off where if we need high performance, we have to compromise a bit on leakage, but that's totally acceptable. The gate length of the FET can be increased in multiple steps to take care of the poly bias to recover leakage when you compare the devices itself. For RVT and HVT, these are formed in regular wells where PFETs are in N wells, unlike in the forward body bias where the PFETs are in P well. So these two devices are allowed to operate only in the reverse body bias mode. So what this will do is this will push the leakage, that is the I off, below the no body bias operation mode, which means the power saving is going to be huge, and the trade-off here is it will cost you a bit of performance, where the speed is going to be a bit slow. So this is how the devices look in 22FDX configurations. Now if you look at this graph where we have the FinFET ion versus I-off with respect to LVT and no body bias and poly bias, the characteristics show us that there is a wide range of frequencies which can be supported, as high as 2.5x. This gives very robust design mechanisms, and the feature of the process itself can be exploited to make the devices work under a wide frequency range at various configurations. For example, by varying poly bias from 0 to 2 volts, 2 to 4 volts, and the forward body bias from 0 to 2 volts, we can get the low voltage operations near threshold in flip well and regular well, as mentioned in the table. Now if we look at the VDD versus frequency graph across the VDD and the threshold voltage and body biasing, we get a huge application space coverage looking at the frequency operation itself. What we have to understand here is we can use a particular configuration of body biasing and device to operate in lower frequency mode with appropriate body biasing. The same devices can be pushed to work a bit harder and work for performance by altering the biasing and make them work in a higher frequency range. This unique feature 22FDX offers, which is going to revolutionize the way we design things, where the device operates in a way it is supposed to, and it can be pushed to work in a high performance mode. So that's the beauty of this technology. What 22FDX also offers is you can choose the best operating point, that is comparison of symmetric versus asymmetric biasing, where not necessarily your PFETs and NFET biasing voltage are identical. So the backgate bias voltage applied to the PFET and NFET can be different, which is called asymmetric biasing, and it provides more design choices and challenges. So we have a short table here where the delay and power comparison of an LVT inverter chain across different body bias applied to the PFET and NFET is tabulated. So if you look at the table, we can achieve a performance improvement of 40% and a leakage impact of 502%, which means essentially greater performance than a symmetric plus minus 1 volt bias, and lower leakage than a plus 2 minus 2 voltage, which is again a symmetric when it comes to the leakage a symmetric bias applied at plus or minus 2 volts. So essentially the sweet spot for maximum performance happens to be an asymmetric bias voltage, which is 1 volt, plus 1 volt and minus 1 volt for the PFET and NFET respectively, which is asymmetric bias, rather than a symmetric plus 2 and minus 2 volt bias, which increases the leakage by orders of magnitude of only 9 magnitude for only 9% of delay improvement. So this is a very important feature the process offers, which can be used in a very positive way to improve design efficiency. If we look at the standard cell beta ratio across body bias, One of the challenges for choosing the correct beta ratio for the standard cell IPs is to consider all possible biasing conditions to be taken care while deciding the beta ratio, width of the PFET versus width of FinFET for a particular cell family. So the figure here illustrates the beta ratio versus the change in inverter chain delay compared to its minimum, which helps in deciding the beta ratio, giving minimum average delay across different backgate bias conditions. Choosing the appropriate PVT corners become vital. Applying reverse body bias to PFET, the delay increase is exponential with very less leakage reduction. On the other hand, applying same amount of reverse body bias to an NFET yields exponential decrease in the leakage with less degradation to performance, thus producing better PPA at SOC level. So choosing the correct bias voltage to be supported for IP characterization is crucial and requires the analysis of delay and leakage trade-offs across different VTs and bias. So thus identifying optimal leakage points and right design methodology to choose between symmetric and asymmetric bias is the key to performance of the design. Moving on to SOC implementations and solutions. In the early phase of design cycle, the top level architecture on biasing needs to be finalized, like which sub-blocks are to be forward body biased and reverse body biased. It is not always possible to directly convert a forward body biased block into a reverse body biased block. That requires design re-implementation. The body bias connections are to be specified in the IEEE 1801 power file so that all of the tools can handle the power policy chosen in an efficient way. Again, we have to keep in mind that for higher performance applications and low voltage operations, LVT, SLVT devices in flipped wells that is forward body biased to be used, and mixed VT implementation between the LVT and SLVT where we can use both kind of devices is very much possible, whereas for the low leakage applications where the leakage power has to be absolute minimum, we can use the HVT and RVT devices in a reverse body bias configuration with conventional wells. Again, here a mixed VT implementation is possible between the HVTs and RVTs. Both the kind of devices can be used in the same block. Of course, separate antenna cells for backgates are needed to be placed in additional capacity in addition to the bias tap cells itself. Mixing between flipped wells and conventional wells with deep end well spacing is possible. Extra routing resources are required for the bias connections in that case. Again, the forward body bias, reverse body bias performance power optimization, where the body bias value decision has to be a new option when it comes to optimizing the overall SOC solution. So what is recommended is to decide the body bias value in the beginning itself to avoid later major decisions. We can add the body bias as one of the variables for optimization to meet the design spec itself. So we can see a few figures here where the SOC solutions have been discussed, where bias tap cell placement and bias power routing has been demonstrated. This has been already been executed, and we have already taped out quite a few test chips using these very options, these very implementations and SOC solutions. Now, after the implementation, let's see some of the results that we got and how the PVT corners were selected. So essentially the PVT corners in figure 1, they became the PVT-B corners, where B is the body bias voltage for P-well and N-well. So design needs to be timing closure to complete with the below corners when forward biasing is applied. So these were the carefully selected PVT corners for the design implementation. Now figure 2 shows a 4850 mm² memory chip, which has approximately about 500k tap cells and 5 million gates. So we ran the power simulations, static power simulations on this particular chip. Figure 3, table 3, it shows the power consumption of only the filler and the tap cells under static conditions, and the total power consumed by the memory chip at various P-well voltages, that is the bulk voltages. The analysis was done using Red Hawk, which is an EMIR tool provided by ANSYS. So if you look at the P-well voltages for -2, the switching -2 volts, the switching and the leakage power in the tap cells was approximately 145 milliwatts, whereas the total power in the chip in watts was about 4.7 watts. When you look at different voltages of the P-well, you can see as we drag down the voltage of the P-well from -2 volts, rather pull up the voltage of P-well from -2 volts to 0 volts, you see a drastic reduction in leakage power in the tap cells, as well as the overall power consumed, as high as 50% drop in power. If you look at case 4, where the P-well voltage is 0 volts, the leakage power in the tap cell is about 35 millivolts, and the total power consumed is 2 watts. A very similar chip, which had a comparable number of gates and tap cells in 14LPP, gave us a power consumption of 3.8 watts, which means again we see almost 40% reduction in power consumption. So this is why 22FDX process is suitable for low voltage applications. They have better electrostatic control over the channel, even at lower operational voltages, very stable performance, improved DIBL and saturation slopes, reduced leakage, loss by a good amount, enabling longer battery life, lower operating voltage, which means reduction in dynamic as well as leakage power, a wide range of back biasing. Again, this means better VT modulation, ensuring discrete power performance, optimized operating points, and an undoped channel for better carrier mobility ensures better performance as lower voltage, also compared to the planar bulk devices. So all low power techniques applicable, same as the planar technology, which is clock gating, multi-VT libraries, static and dynamic power switching, retention modes, adaptive voltage scaling, dynamic voltage and frequency scaling, static and adaptive body bias, gate length biasing, split supplies. These are the various techniques which makes this process very attractive when it comes to being the choice for low voltage, low power applications. Figure 1 shows the delay variation at low voltage for a DX forward body bias device around equal to 2x lesser than that of a FinFET device. So this less delay variation is again a very key factor when it comes to 22FDX as a choice for low voltage and IoT applications. So in summary, 22FDX has wide application spectrum. It's best suited for IoT applications, as it can achieve ultra low voltage operating with the forward body biasing configuration and ultra low leakage with the reverse body biasing configuration. It covers high-end smartphones, processor application with the forward body bias and SLVT devices. Additional trade-offs available for designer in terms of symmetric versus asymmetric bias, single versus multiple beta ratios, optimal bias point, that is the PVD selections, and the forward body bias versus overdrive voltage for frequency push. This is the on-demand performance where on application of an overdrive voltage, the device just wakes up, performs really quick, switches really quick, and then goes back to sleep. Then, of course, as for SoC implementation, we require bare minimal changes in the existing flows and tools and methodologies. Invecas has already provided solutions to address the changes needed for SoC implementation, and we are partnering with all the industry EDA vendors to make sure that this process goes through smoothly, giving us excellent results. I would like to thank the management of Invecas, GlobalFoundries, and Ansys for this opportunity to present this webinar, and contributors, Naga Prasad Panna of Invecas, who is our Foundation IP team lead. Srikanth is our SoC implementation lead, and Shankar from Ansys for tool support on the Red Hawk side.
Thank you for joining us today to learn more about GlobalFoundries, how to maximize 14LPP and 22FDX performance and power savings with Invecas IP. More information about 14LPP, 14nm FinFET, 22FDX, and 22nm FDSOI technologies can be found at GlobalFoundries.com.